Okay, so I guess we are live. I welcome you all to my YouTube channel. That is Suchit Sharma. That's my name. Uh, let's continue with week 5 and complete the remaining portion. I guess we would be able to uh, complete 30% of week 5 today. So, what we would be covering right now is functional dependency theory, right? Before I do that, let me check whether the you know whether the stream is going on perfectly or not. Are there any problems? Are there any issues? So what we would be covering right now is functional. Hmm. So this is why we check. I just saw that I did not share my screen. Now that I have shared my screen, it's visible. It would have been really bad if I would not have done it. So again, a gentle reminder to subscribe, and let's start with the you know week 5. Okay, functional dependency theory. Functional dependency theory. So basically, there are these three axioms known as Armstrong's axioms. They are just wait a second. Yes, we can infer the new given a functional dependency f. I guess I'm getting okay. Given a functional dependency f, we can infer new dependencies by Armstrong's axioms, right? We can infer new dependencies by Armstrong's axioms. Let me do it, mark it in another color. Okay, by Armstrong's axioms. So the first one is reflexivity, meaning if beta is a subset of alpha, then alpha is the functional dependency of beta. Meaning, if beta is a subset of a given set alpha, then beta is also functionally dependent on alpha, right? Let me use another color. Mhm. Somewhere like something like this. If beta is a subset of it's beta. Okay, so if beta is subset of alpha, then then beta is also functionally dependent. Okay, the beta is also functionally dependent on alpha, right? If you find it hard to remember, just remember the curve. Both the curves point towards p. Okay, now augmentation. If alpha is the functional dependency of beta. Okay, alpha is a functional dependency of beta, then gamma times alpha is also the functional dependency of gamma times beta. Meaning, uh, let me explain this to you in the most basic form. See this as a mathematical equation. Remove the arrow and consider it as an equals to sign. You can simply cut gamma. You can simply cut gamma, and again you would get alpha is equal to beta in this case. Okay, but that is not how you see things in D.B.M.S. That is not how you see things in D.B.M.S. In D.B.M.S, if this is the case, if this is the case, means let me draw a table. Let me draw a table. I hope they allow me. Okay, so they do not allow us to do that until we pay them. So let's say we have a you know table having alpha here, alpha, and one having beta, right? So there are tuples where you can identify. There are these tuples available in this table by which you can say, okay, yes, beta is functionally dependent on alpha, or alpha is the functional dependency of beta, right? Once you see this, you can also write this, right? Alpha times gamma, alpha times gamma, sorry, my mistake. This alpha gamma meaning, this alpha gamma would mean, let me change the color and extend the table. Alpha gamma would mean this, here and one here. Okay, what I'm doing, I'm extending the table to make you understand, right? So gamma alpha and gamma beta, right? Now what you need to check now is the green color available? Yes, the green color is. So you need to check this much as a whole unit and compare it with this much, right? Now this is a whole unit. Let's call it x, and this is a whole unit. Let's call it y. I think it is not visible. Okay, now it is visible, right? Let's call it y. Okay, so now this whole unit x is the functional dependency of y. Understood? Basically, what you are doing is you are appending a gamma column in front of alpha and in front of beta. That's what this means. You can append it on the either side. Gamma alpha is equals to alpha gamma, right? You can also write it as this, right? Alpha gamma, alpha gamma is the functional dependency of beta gamma, right? Even this is true. Even this will stand true. Okay, let's move forward. I have to erase this rather than deleting it, because erasing is currently what I need. And transitivity. So in maths one, you would have you would have known this thing. Let's not read this. Let me remind you what you have learned in maths is, if a belongs to if a belongs to some function, if a belongs to some function x, I think that's a mistake. The equation is something like this. Let me type it here. It's something like, something like this. If ab if ab belongs to some function x, and bc, bc also belongs to x, then ac must also belong to x, must also belong to x. Okay, there's an x here. I hope you understand, right? This is what we were taught. Now let's come here. Let me check this once. Is the stream going on perfectly or not? Must also belong to x. let me just check how much the voice is coming. Okay, it's more than sufficient. It's more than sufficient, but let me be a bit more loud so that you can hear it. Right. So in here in functional dependency, while reading Armstrong's axioms, what transitivity would mean is that if alpha is functional dependency of beta and beta is functional dependency of gamma, it is that alpha is also a functional dependency of gamma, right? So if this equals this, so there are three, there are three things. If alpha, beta, and gamma, if alpha is the functional dependency of beta and beta is the functional dependency of gamma, this means alpha is directly the functional dependency of gamma. That's what this means. Okay, quite simple and easy. Let's delete and uh, continue. These axioms can be repeatedly applied to generate new functional dependencies and added to the function, right? A new functional dependency obtained by applying axiom is said to be logically implied by f. Okay, this is an important line that tells us about the definition of logically implied, that any new functional dependency obtained by applying the axioms, right, would be said as this plus this would be said as logically implied. Okay, the process of generations of functional dependency terminate after finite number of steps, and we call it closure set. So while you keep on adding functional dependency to a given set f, there you would reach a point where you can no longer add or generate any functional dependencies, which would be called as the closure set. Okay, f plus would contain all the functional dependencies that are possible. This is set of all the functional dependencies that are logically implied by f, right? Set of all the functional dependencies logically implied by f. Now, this is what you should know, that these axioms are sound and these are complete, meaning they generate only functional dependencies that actually hold, and eventually they will generate all the functional dependencies that may hold. Okay, prove the axioms from the definitions of prove the soundness. Okay, functional dependency, closure set of functional dependencies, right? So let me do this. So basically what the question would come is you need to use Armstrong's axioms to find the functional dependencies, all the possible functional dependencies that will hold, right? So you are given a set f having the following functional dependencies, right? Now once you go to the transitivity statement, or the transitivity axiom in the Armstrong axiom, you would find that since A belong to B and B belong to C, then A must also belong to C, right? Okay, so you add A belongs to C to the closure set, right? Now let's say, is reflexivity left. What you basically do is you check each and every axiom one by one and add the functional dependency that is not there in the set f. Okay, and once you can no longer add any functional dependencies through these three, it is called the closure set. Okay, closure set of functional dependencies. Let's see this. Okay, so we are given a relation that has this. I need to, you know decrease the size of it. That has this, the relation having the following attribute. You also have a function f. You also have a function f that has the following. That is a set of the functional dependencies that already exist. That a is a AFD. Let me call this sign. This sign from now on we would be calling it as implies. Okay, a implies, right? The word implies, implies, the word implies would be used instead of arrows as, or let's just call it arrow, right? Let's just call it arrow. We would be calling it arrow. A arrow b, a arrow b, ascending order of height. Okay, that's what we achieved. uh, let's go. A arrow b, there's also an a arrow c, then there's cg arrow h, cg as a unit, meaning see, you can do this. Cg arrow h means both the tuple, or sorry, both the attributes c and g respectively have to come together to form the functional dependency h, right? Individually c cannot be functional dependency of h. Individually, let's say we talk about c can't be, okay? There is no way c individually can be functional dependency of h, and there is no way that g can be independently functional dependency of h. It only works when c and g come together as a set, and then they become the functional dependency of h. Okay, let me do this. Okay, so it is more understandable, right? Let's remove this. Now same is the case with I, that cg comes together to arrow I, b arrow h. Okay, that's what we are given it. Now what you need to find is f plus, the closure set. By transitivity, since a, mhm, what do I do for this? Yes, this is better. Mhm, good. uh, Now what we need to find is this, right? The closure set f plus. Now since a since a is the functional dependency of b, and b here is the functional dependency of h, this would imply that finally a would also be a functional dependency of h. That is, a arrow b and b arrow c, implying a arrow c should also exist in the closure set, right? Now since a is a functional dependency of c, so instead of cg, what you can write is, instead of cg, what you can write is ag. It would be the same. It would be same. uh, Now cg, yes, there is one more thing that I need to cover is, although that individually cg, the individual elements of the set cg may not address, or may not be the functional dependency of h. However, let's call this a unit x, right? Let's call this a unit x for the for the sake of it, we would be calling it the unit x. It's not wrong wala cross, it is x. Okay, now x as a unit is a functional dependency of h, right? Also x is a functional dependency of I, right? That's what we are given with. Now you must understand that although left hand side cannot be decomposed, right hand side can be. Okay, left hand side of a functional dependency cannot be decomposed, but the right hand side can be. So this H and I can be clubbed together to form X being the functional dependency of HI, right? So decomposition can be done on the right hand side of the functional dependency arrow, but not on the left hand side. Understood? Let's move forward. That is why here you can see CG equals to HI because of CG arrow H and CG arrow I exists. So we are clubbing H and I together as they are on RHS. Okay. So this is like a pseudo code of finding functional dependencies in Python function or in any higher level languages. You may read this. I am skipping this for now, as this is of no use for me. If it comes and if I have to use this later on, I would be returning to it immediately. Now, uh, now apart from the axioms that Armstrong gave us, there are some additional derived rules that we made by basically messing with the axioms, right? Or they are logically implied by, when axioms hold true. If axioms hold true, these additional rules also stand true better. So union, if a if alpha arrow beta and alpha arrow gamma holds, if both of these hold, then alpha can be directly clubbed with beta gamma. That's what I said with the upper one, you know the this one, this CG one. If if CG arrow H is if CG arrow H exists and CG arrow I exists, then CG arrow HI is the same. You can simply unite them, club them. The logical word, the derived rule name is union. Also, converse of this is also possible. You can also do converse of the same. Just a second. Right. If you want to do converse of the same, that this holds, alpha implies beta gamma, then alpha would imply beta individually and alpha would imply gamma individually. Okay. Now let's go to pseudo transitivity. Pseudo transitivity means if alpha implies beta and gamma beta implies delta, then alpha gamma implies delta, right? So I think what they have done wrong here is they should have provided this slide before doing this, right? Before solving problems on closure sets. No issues, no issues, right? The above rules can be inferred from the basic axioms. Yes, the above rules can be inferred from basic axioms. Okay, prove the rules from basic axioms. Yeah, 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 that's the same. So what did we learn? What's the extra thing that we learned? One is the union, other one is decomposition, and the last one is pseudo transitivity. Okay, closures of attribute set given the attribute alpha, define the closure of alpha under F denoted by alpha plus as the set of attributes that functionally determine alpha. Okay, let's leave this. Closure of attribute sets example. Okay, okay, okay. This is what we need. Okay. So what we did on the set F, what we did on set F, it's the same, right? So for set F, right? For set F plus, that is F plus was the closure set, right? F plus was the closure set. Let me remove this for here for a second. F plus was the closure set. Similarly, let's assume that we have the following attributes in a given relation, right? These are the attributes that exist. Let's take a singular attribute A. Okay, let's take a singular attribute A. Now, let's we can also find just like finding closure set for F, we can also find a closure set for A. How is it possible? How do we do it? We will be seeing it right now. This is possible. Okay, even this is possible. Let me put tick marks so that no one gets confused. Even this is possible. Uh, Before explaining this, just give me 1 second. Okay, I need to check one thing. Okay, so was some error, issue with there was some issue with the internet. I don't think there would be any issue right now. Let's start. Okay, so let's say we want to find. Mhm, mhm. Let me read this. This is the set of functional dependencies that exist, right? This is the set of functional dependencies that exist. What we need to find is AG plus, the superset or the closure set of AG. So let's take AG. Mhm. Let me bring my pen. Okay, so what we are doing is black pen. Okay, what we are doing is finding AG plus, right? What we need to find is AG plus. So you need to go through the set many times. Okay, so let's start with A. A is a function. AG would mean firstly AG plus would mean let me start from here. I need some space to write it properly. This is better. Okay, so for AG, how do we find the superset or the closure set of AG plus? That is AG plus. Okay, so let's start by finding functional dependencies. We know that A itself is a subset of the closure set, right? A itself is a subset of the closure set. Meaning, if we consider this as a unit, this would mean that AG would be there in the superset, or the closure set. AG would be there in the closure set. Now let's take A. That was the initial stage. Now let's take A. Okay, a bit bolder. Mhm. This, right? Now A has the following functional dependencies, right? A has the following functional dependencies, and through this one, A also reaches these two. Okay, A also reaches these two, meaning the superset would also consist of this, right? Firstly, let's consider the simple one, AB and AC. Since they are the functional dependencies, we can simply add A, we can simply add B, as they are the functional dependencies, and then finally G. Okay, now since CG equals to AG, as we told earlier, due to this one we can simply assume that A must also reach these two. A can also reach these two. We can also add H and I. Okay, we can also add H and I. So A, B, C, G, H, and I. So this is the same as this, the final result that is provided. Okay, now is AG a candidate key? Is AG a super key? Is AG a subset of super key? Let's find out. Okay, I hope you understand how you would find the superset of any given attribute, or set of attributes, or composition of attributes. This was a composite function. Okay, this was a composite function, or a composite key. All right, let's go further. Closure of attribute. What are the uses? Okay, there are several uses of closure algorithm. This closure algorithm is used to find the super key, whether a given whether a given key is super key or not. If alpha is a super key, to see if alpha is a super key, mhm, we compute alpha plus, that is closure set of alpha, and check if alpha plus contains all the attributes of R. So in the previous example, we can say that AG is a super key. AG is a super key since the closure of AG results in the exhaustive set of the relation, right? AG plus covers the attributes. AG plus covers each and every attribute that exists in the relation R. Hence, AG is an super key. Now we can also check functional dependencies to check if a functional dependency alpha arrow beta holds, or in other words, if is in a closure set of F. Just check whether alpha plus. So first you will need to find alpha plus, whether beta is a subset of closure set of alpha. Okay, so every dependencies that exist in alpha would be alpha plus, and you should just simply compare whether beta comes in that set or not. Computing closure of F. Okay, for each gamma that is subset of relation R, we find the closure gamma plus, and for each S that is subset of the closure set of gamma, we output the functional dependency gamma is a subset gamma arrow S. Okay, so basically what we are doing is we are checking for functional dependencies. We are checking whether gamma is a functional dependency of S or not. So immediately we will be finding the closure set of gamma, and every time S becomes a subset of gamma plus, we say that Gamma is a functional dependency of S. Okay, let's move forward. Decomposition using functional dependency. Boy's code normal form. So this is where professor lacks. Okay, so let me show you how many normal forms in normalization exists. Okay, let me find the images. Okay, normal forms, how many normal forms are there? You can see these many normal forms. Okay, you can see it by the bullseye arrow. There are 6 normal forms. However, the professor jumps directly from the first normal form to BCNF, and later on he again turns back to the third normal form. So the basic order should be in this way. This is the correct order. What professor does is he goes from here to here and then here to here. And any newbie who doesn't know that this is a thing in D.B.M.S would confuse the BCNF as a second normal form and then move on to the third normal form, and eventually would not even know that there are total 6 normal forms. This creates confusion in students. However, I told you this because I got the knowledge from extra sources. Okay, let's start with the boys code normal form. The boys code normal form. So we have already told what trivial is and we already told what super key is. So a given relational schema R is in boys code normal form. Given relation given relational schema R is in BCNF boys code normal form. It's too lengthy to call this boys code normal. Initially I called it Beyonce Cody, but later on I corrected it. So boys code normal form. So any table R is in BCNF with respect to the functional dependency set F, right? F has all the functional dependencies, right? F has all the functional dependencies. Where alpha is a functional dependency of beta, alpha is a subset of R, beta is a subset of R, at least one of them, then at least one of these holds, right? Okay, for boys code normal form to exist, that alpha arrow beta is trivial, right? Is trivial, meaning that beta is a subset of alpha and alpha is a super key. So all in all, what you need to check is, let me erase this much. What you need to check finally is this: whether beta is a subset of alpha or not, and whether alpha is a super key or not. These are the two conditions that you need to check. If both of them checks true, then it is in boys code normal form or it is BCNF. Okay, let's move forward. Example schema not being in BCNF. Uh, mhm. Example schema not being in BCNF. Mhm. So instructor department contains the following attributes: ID, name, salary, department name, building, and budget. Because the non-trivial dependency department name arrow building comma budget holds on okay. So department name, what this example shows us is that although one condition is satisfied, that department name I'm sorry for this. That department, okay, is a non-trivial dependency. However, department name is not a super key. Since it is not a super key, this is not considered BCNF. Okay, so both of them should hold true. Both of them should hold true. Lossless join. So basically, this is the proof that BCNF ensures lossless join. Let's see this. If we decompose a relation into two separate relations, R1 and R2, if we do that, let's say we have R, we decompose it into, you know, R1 and R2. Let me write it once. R1 and R2. The decomposition, the decomposition is lossy if R is a subset of natural join, right? And lossless if R is equal to this. So basically, what this says is, okay. So this is basically something that we learned before. That once you divide something into two separate tables, and you perform this natural join between this infinity one, it must result in the table itself. Okay, if you perform this, it must result in the table itself. If it results in the table itself, it is called lossless, and if it does not, it is called lossy, as mentioned here. To check, let's move forward. To check for the lossless joint decomposition using the functional dependency set, the following must hold true. Union of attribute must be equal to, okay, this is something good, and intersection of the attributes that should be null. Meaning, once you unite the two tables, it must result in the original table itself. However, there must not be a single tuple, a single data common between the two tables. Okay, common attributes must be key for at least one relation. Okay, so let's call this x. Okay, let's call this function x. If r1 intersection r2 or r1 intersection r2 are functionally dependent on r1 and r2 individually. Okay, so what this is telling is, this. Let me show you here. It would be better if I show you. This is the previous slide. hmm I think one before that, the one before that. All right. See. So what this says is, once we deconstruct the instructor with department table into two separate uh, two separate tables, right? Once we do something like this, what the third one is saying is, there must be at least one attribute common between them. There must be at least one attribute common between the instructor table and the department table. So what is common between them? Department name is common between them, right? See this. Department name is common between them. है ना? So let's go to our original PPT. That's what I This is what I showed you. Hence, BCNF ensures lossless join. Now, once you consider these three conditions and compare it with Boyce code normal form, meaning alpha beta is trivial, beta is a subset of alpha, and alpha is a super key, meaning common between the two. If it is super key for relation, it is present in both the tables. This finally results in BCNF ensuring there is lossless join between the two subtables formed by a given table. BCNF dependency preservation. Okay. Uh, Constraint including functional dependency are costly to check in practice unless they pertain only one relation. If it is sufficient to test only those dependencies on each individual relation of decomposition in order to ensure all the functional dependencies holds, then the decomposition is dependency preserving. Okay, so basically we are dealing with small tables and small relational schemas. Once the table is in hundreds and millions, it's really hard to check whether the table is lossless or not, or whether it is BCNF 1F or not. So what we need to do is we need to find a way to minimize the time taken to compare two different attributes so that we can find a given statement, so that we can find a given relation between them. Okay. It is not always possible to achieve both BCNF and dependency preservation. Okay, that's what is this saying is, either you can sometimes either you can get BCNF, or sometimes either you can get dependency preservation. Okay, key is that satisfy BCNF, but Z implying C violates. See this, CS implying Z satisfies the BCNF conditions. However, Z implying C violates it. So either you can get preserved data, preserved dependency, or you can achieve BCNF. However, in this case, you are not getting both. Let's move on to the third normal form. One more thing. There is this channel named as Gate Smashers, a really good channel through which you can learn. Even I learn from his lectures. Okay, he is a really good teacher, and I advise all of you to at least once visit this channel. Okay, if you're not able to, it's okay, since my channel is always there. You can always come back to my channel and watch the videos. All right, let's go. uh, a schema is in third normal form if we find a subset beta from the closure set of all the functional dependencies, such that alpha is a functional dependency of beta. uh, the following must hold that alpha arrow beta is trivial, alpha is super key for the relation, and each attribute A in beta minus alpha is contained in the candidate key for R. Okay. If the relation is in BCNF, it is in 3NF form. Since BCNF is one of the first two conditions, above must hold. Okay. The third condition is minimal relaxation of BCNF to ensure dependency preservation. Okay, so 3NF uh, 3NF ensures that we have dependency preservation. Okay. Now, why do we are normalizing the data too much? We have learned first normal form, third normal form, BCNF, and as we know that there exists many other form of normalization. Why are we learning this? What are the goals of this normalization? So it helps us decide whether a relational scheme is in good form or not. In the case that relation scheme is not in a good form, we shall decompose it into a set of relation schemes R1 till Rn such that each relation scheme is in good form. The decomposition is lossless joint decomposition, and preferably the decomposition should be dependency preserving. So 3 points we must keep in mind is, Firstly, it should be in good form. Secondly, let me do this line properly. Firstly, it should be in good form. Secondly, lossless join should happen. And thirdly, it should be dependency preserving. Okay, three conditions that must check true. All right, let's move forward. Problem with there are some problems with decomposition. There are three potential problems that they have listed here. It may be impossible to reconstruct the original relation. Meaning that a table may not always be lossless join possible or compatible. Meaning there are a few tables, once you decompose them, they can never be reconstructed into the original relation. Dependency checking may require joins. That is true. Some queries become more expensive. What is building for an instructor? Yes, yes, yes. Trade off. Must consider these issues versus redundancy, right? So either you can consider these issues, or you will have repetitions in your data. You This is the trade off that you finally have to check, or you finally have to choose from these two. How good is BCNF? There are database schemas in BCNF that do not seem to be sufficiently normalized. Okay, consider a relation this, let's call it X. Consider a relation instant info which contains the attributes ID, child name, and phone. Okay, where instructor may have more than one phone and can have multiple children. Okay, so this is the ID of the instructor, and the children coming under that particular instructor are David and William, and David and William individually have two phone numbers each. Okay, so this results in this huge table. This is in BCNF form. However, this is not a data that we anyone would like to work with. Okay, there are no trivial function dependencies, and therefore the relation is in BCNF. Right? Insertion anomalies. That is if we add phone number to 999, we need to add two tuples, right? So every time we add something new, every time we append, every time we update the phone number in the instructor info table, we would have to update it twice. Okay, so let's say this is the number. Okay, so this is the number of instructor himself, right? That he has. See, these two are same. Okay, these two are same. So this is the number of instructor that he has given to the students or the children. This is the same, this is the same, right? So every time, let's say I need to change this number into something new. If I want to change this number into something new, what I would have to do is change the number change this number two times. Okay, once here and once here. If there were 100 children, we would have to update it 100 times. That's a big problem because you know come on, it's really hectic to do same function 100 times, right? And we would have to change, add, append, whatever you need to do, keeping every child in mind. Therefore, it would be better to decompose the instructor info into two sub tables, one being instructor child and one being instructor phone number, right? This suggests the need for higher normal form, such as fourth normal form. And here, this is where we conclude our 5.3. I hope this is 5.3. Yes, the relational database design 3. Okay, let's solve the problems. What is a set of functional dependencies? A set of, oh, okay, okay. What is the closure set of a functional dependency? What is the closure set of the functional dependency? Black one, right? Is there some other color? Yes, the black one is good. Black one is enough. What is the closure set of a functional dependency? A. A set of all functional dependencies implied by the original set of dependencies. A subset of the original. No, it cannot be subset. It cannot be something minimal set. Right? It cannot be any of these two. Okay. Of functional dependencies which cover the original set of dependency, of a subset of original set of functional dependencies which cover the original set. No. So let's read this one. A set of all functional dependencies implied by the original set of dependencies. Yes, this may be true, right? This may be true. Let's uh, let's put this as our answer. Let's go back. Choose the correct statement about Armstrong's axioms, right? Armstrong's axioms. Armstrong, yes. Reflexivity, augmentation, and transitivity. Reflexivity, augmentation, and transitivity. They can generate functional dependencies which may not always hold. They always generate functional dependencies which are applicable on the relation. They may not be possible to generate all not be possible to generate all the applicable functional dependencies using them. They always generate complete set of functional dependencies. Okay, so what we have learned here is what we have learned in from the table is that they are sound and complete. So they generate only the dependencies that actually hold, and eventually they would generate all the functional dependencies that hold. Okay, meaning that they can generate functions which may not always hold. No, this is not true. They always generate functions which are applicable in the relation. I think this is true. It may not be possible to generate all the applicable no, it is all they always generate the complete set of functional dependencies. Right, yes, this is true. Let's move forward. Which amongst the Armstrong axioms applied in the statement below? Okay, which amongst the Armstrong's axioms is applied in the statement below? So if A arrow B and BC arrow D, then AC arrow D. Okay, so if A equals B and B equals this is what we do. Pseudo transitivity. Transitivity. I need to work on my pronunciation. This is not transitivity, this is pseudo transitivity. All right. So let's put this as true. We just read this here. Let me bring it here. Pseudo transitivity. If A holds and gamma holds delta, then alpha gamma holds right. Let's move forward. Which among the Armstrong's axioms apply in the statement below? If A arrow B and AC arrow BC, then I think it is augmentation. Which one is it? Augmentation. Yes, it is augmentation. Let's move forward. Consider the given relation having the attributes A, B, C, D, E, A, B, C, and H. Okay, so 6 attributes. And functional dependency set. Okay, so this is the set of functional dependency. Let me zoom out a bit. Okay, so this is good. The set of attributes, and this is the set of functional dependencies. So what is AC plus? What is the closure set of AC? So closure set of AC would be closure set of AC plus, right? So they automatically imply that A and C are the part of it, right? A and C are part of it. AC is the part or the subset of A and C a whole closure, right? After that, let's go to FD and check. Since A arrow H, we can also add H in the given, in the given equation, and H holds B, and H holds B. Sorry, my mistake, my mistake. CH holds B. CH holds B, right? So if CH, let me check. Yes, CH holds B. Yes. So since we already have CH here, we can also write B. We can also add B into it, right? A C H and B. Now GC implies B, right? But there is no way to reach till G. So I think this is the exhaustive set, and hence option B is true. Option B being true. Let's move forward. Consider the given relation with the following attributes and the following functional dependencies. Let's find the correct options. Is AGI a candidate key or not? Or is AG a super key or not? Is AG a primary key or not? Or will A plus generate A, B, C, I or not? Right? So let's check the first one. Give me 1 second. Give me 1 second. Just 1 second. Okay. Yes. Let's check AGI, whether AGI is a candidate key or not. Okay. So we have uses here. Plus, let me show you this. This image is really, something you should watch. This is that every primary key is an candidate key. Every candidate key is a super key. So in the PPT we have only super key. We have only one thing, that is testing for super key. We have no such thing as candidate key, checking for candidate key, right? So what we can do is we can find whether it is super key or not, right? AGI is a candidate key, so let's write AGI, AGI, and from A we can measure BC, so we can also write A B C G I, A B C G I. From GC, that is this one, we can measure H. So finally we can write A B C G H I. Okay, A, okay, A B C G H and I, and this is an exhaustive set, right? 1 2 3 4 5 6, 1 2 3 4 5 6. So as it is a super key, it is also a candidate key. Yes, this holds true. Let's go for the other one. Okay, so this is something which is darker, right? Let's check for AG. AG. AG from I won't be writing this, huh? I won't be writing this time. From A we can measure BC, and since we are measuring BC, we can also measure H. So yes, AG is a super key. AG is a super key. Is AG a primary key? Yes, we can also consider it as a primary key if from this Venn diagram, I think, did I remove the Venn diagram or did I keep it? I don't remember. From the Venn diagram, if anything is super key, it is automatically a primary key. So yes, AG is also a primary key. Let's go to A plus. Let's check for A plus. Now A plus would measure A plus would measure BC, and from B I can measure I. So obviously A would measure itself. It would measure itself. Then it would be measuring BC, and it would be measuring I. And I know I did make a mistake here. I would be removing G. Don't worry, I would be removing G. This is not this is not right. Okay, this much is correct. These four. So yes, all the options are correct. Hmm. Choose the appropriate condition options necessary for lossless joint decomposition of table R1 into R1 and R2. Okay, so I think you remember what it is written or not. It is given in the PPT itself, proving that BCNF ensures lossless joint. It is given here. Now consider the statement. There is always a way to there is always a way to decompose a relation into smaller relations such that each new relation is in dash and the functional dependencies are preserved. Which among the following options will make the above statement correct? So such that the functional dependencies are always preserved. So it is 3NF and not BCNF, because BCNF does not always guarantee about, it is not always possible to achieve BCNF and dependency preservation, right? So it does not guarantee dependency preservation. However, 3NF form does. uh, 3NF form is minimal relaxation of BCNF to ensure dependency preservation, as it is written here. Choose the correct statement. The schema is said to be completely normalized if it is in BCNF. I don't know about this. Increase in the query cost of specific queries, disadvantage of decomposition. Yes. If relation is in BCNF, then it is also in 3NF. Yes. The attribute set closure can be used to find candidate key. Can it? The set closure one. Let's find the closure of sat attribute. It is used to find super key. Since we can find super key, we can also find candidate key, because candidate key is a subset of super key. Yes, so hence it is true. Consider the relation R with the following attributes and functional dependency A with the following functional dependency set with the following functional dependencies. How many candidate keys are there in this relation? Ooh, that's a lengthy one. That's a lengthy one. How many? What do you say? So we can go this closure of attribute method. We can use the closure of attribute method, or let's just write the question here. Let's just copy paste the question and find the easiest way that comes out, right? Let's find the easiest way that comes that Google or Bing Baba gives us. So this question is provided or not? What happened? Okay. So basically, I would be trying to find out the number, the number of super keys, and to find out the super keys, it's just simple. We compute a plus, alpha plus, and check if alpha plus contains all the attributes or not. Okay. See, we would be checking for A, B, C, G, H, I individually. So A maps B, and that's it. You need C to map further. So A plus is out of the equation. Go for B. Let's go for B. B, even B is out of the equation. Uh, however, if you to measure individually, I guess A, B, C, D, E, F, G, everyone is out of the equation. You need a set of two. You need a composite key to keep it as a candidate key. So let's talk about A, B, C, A, B, C. So B, C covers G, I, and G covers C, H. Meaning G, H, I is covered in A, B, C. In the closure set of A, B, C plus, in the closure set of A, B, C plus, you get, okay, let me do this. In the closure set of ABC plus, you get GHI, and which is the exhaustive set R. So ABC is a super key, and hence it is a candidate key. Let's try to find another. Let's try to find another. Let's try for, how do I say it? A and G. Let's talk about A and G. If I do a closure set on this, if I add a closure set on this, so A maps B, G maps CH, and BC maps I. Again, we can map each and every single one of them, meaning they are candidate key. Okay, I think is there some other way to map it through H and I? I don't think I can map it through H and I. So there are two candidate keys that are possible, or one. It's either two or one, because I have doubt, as you can map C and B and C through G, and again G through B and C. So let's check the answers. What happened? Let's check how much. 8 out of 10. This is really good score. This is a real good score. Let's check where did we go wrong. Or okay, no. R1 cross R2 R1 intersection R2 should be null set. That was true. I don't think choose all the appropriate condition necessary for lossless join. I think we were correct here. Why, why are they telling us we are wrong? What is it? Lossless join. Okay, so it must not be null. Okay, so there must be something common between them. Okay, there must be something common between them. I misread the statement and hence I was wrong. Okay, AGI is not a candidate key, it is a super key. Good. Let's move forward. Okay, so I would be taking a break of I guess 10 minutes now. You can skip till the part where the screen is no longer black. Okay, and we would be starting 5.4 now. Okay, so I'm back. That was all the rest that I needed. As you can see, the time it's 12 o'clock. Still, I will be completing this video. I will be completing 5.4. Without that, I won't be sleeping. Okay, let's start. So I completed 5.3. Let's move on to 5.4. Right. Relational database design. Fourth lecture. Uh, what are the module objectives? We need to learn algorithms for the properties of functional dependencies. Okay, algorithm for functional dependencies. So this is attribute set closure. Okay, excuse me. Okay, let me be doing this here. Okay, uh, I have a relation R with the following attributes and have the following functional set with the following functional dependencies. What I would be finding is AG plus. Just give me 1 second, right? Is it the correct one or not? Yes, it is the correct one. Okay, so these are the functional dependencies. These are, mm, let me change the color of the marker. These are the attributes in the relation. These are the functional dependencies in the set F. And what we need to find is the closure set of AG. So how do we find closure set of AG? So the immediate result that we get is AG itself, because uh, A is a subset of the closure set itself. Okay, A itself is the subset of closures. The closure set. After then, after that, we using this set, we find out that A is A arrow C and A arrow B exists, which means we can add B and C into the result. After that, we see that CG is a subset of AGBC, and CG is implying H. So we can add H into the result set. Finally, CG arrow I exists, so we can add I here. Hence, the result of the closure set of AG key is ABCGHI, the exhaustive set over R, right? Is AG a candidate key? Is AG a super key? See, AG is a super key and hence it is a candidate key. It is a super key because because the closure set of AG is is the exhaustive set of R, is exhaustive on the set of R. AG plus is exhaustive on the set of R. Hence, it is superset. And let me show you this through this diagram. Through this diagram, I can tell that any super key is a candidate key by default. Hence, it is a candidate key. Is subset of AG a super key? Is any subset of AG a super key? So, no subset of AG is a super key because we checked it in the previous, PPT. Let's move forward. Let's move forward. Attribute set closure is okay. So it's the same. Uses the following are the uses of you know set closure attribute: testing for super key, testing for functional dependencies, and computing closure of F. Okay, these are the attributes. sorry, these are the uses of attribute set closure. Now, what's an extraneous attribute? What is an extraneous attribute? So let me show you this. Let me change the color of marker and the size of the width of it. See, if this exists, if the following set exists, meaning that a arrow c exists and ab is an arrow to c, so it is useless to write, it is useless to write ab arrow c when a arrow c exists. We can directly write a arrow c instead of going this longer way, meaning b is extraneous. B is extraneous. Control 4. Give me change the color. B is extraneous, right? So we can remove B and directly write A and C. Usually, it does not happen. It does not happen that we can break down a given functional dependency into we cannot decompose a functional dependency on the LHS, but here we are doing it. Why? Because in the set this statement is provided by default, or we by doing some attribute through closure sets, through many closure sets, we find out that this relation turns out to be true, that a arrow c exists. Hence we can directly write that a arrow c. So do not mistake it as we are as this. Do not mistake it as you know what is it called, the decomposition of the set on the LHS. This thing, this BROC will never exist, has never existed, and is never existing. Okay, na tha, na hai, na hoga. This never happened, isn't happening, and never will happen. Okay, this statement is correct because of A arrow C. That's it. This has nothing to do with decomposition. Okay, let me remove this. Hmm. Okay. All right. A plus is equals to AC in A comma C. Okay. Example. Let's solve another example. Since A implies C, since A implies C and AB implies CD, then C is extraneous in this case. We can simply remove C. Oh, you were thinking, why did we not remove B? Why did we not remove B in this case? Because if we had we removed B, then we would have we would have violated the decomposition law. And as I have told multiple times, and I would say it again, we cannot decompose a data. We cannot decompose a given functional a given functional dependency. So then why C? Why C? Why did we remove C? Because let's call this AB a set X, right? Let's call this a set X rather than AB. This is what it's showing us. Okay, this is what's being shown to us. X is a functional dependency of CD. Now we can remove C on the basis that A arrow C exists. Okay, we have already covered C. We have already reached C through this functional dependency. Hence, we only need D in this situation. We only need to map D in this situation. Understood? Okay, let's move forward. Let's move forward. Extraneous set tests consider a set f on of the functional dependencies and functional dependency alpha arrow beta in f to test attribute a belonging to alpha is extraneous in alpha. Compute set a minus alpha closure using the dependencies in F. Check that this contains beta. If it does, A is extraneous. To test this, just the vice versa. To test A belonging to beta is extraneous. That is, this shows something in LHS is extraneous, and this shows something in RHS that is extraneous. Okay, let me write it for you. This is for LHS, and this is for something that is on RHS. Okay, so to test if something on our right hand side is extraneous or not, we compute alpha plus, we compute the closure set again of the LHS as we did here, now using only dependencies f dash, and where f dash is the set minus the specific functional dependency union alpha arrow beta minus a. Okay, check that alpha contains a. If it does, a is extraneous in B. Okay, now equivalence of sets of functional dependencies. Let's let's come to this later on. Canonical cover or the minimal cover. Okay, the minimal set of FDs. A canonical cover of F is a set of dependencies FC such that all the following properties are satisfied. F logically implies that all the dependencies in FC. FC logically implies all the dependencies in F. No functional dependency in FC contains extraneous attribute. This is an important line. That no function in dependency, no functional dependencies F in FC contains an extraneous attribute. Each left side of the functional dependency of FC is unique, and there is no two dependencies in alpha 1 arrow beta 1 and alpha 2 arrow beta 2 in such that alpha 1 arrow alpha 2. Okay, intuitively a canonical cover of F is minimal set of FDs equivalent to F. uh, okay, it is the minimal set of functional dependencies that are equivalent to F, having no redundant FDs and no redundant part of FDs. So basically, it is the minimal irreducible set of functional dependencies or the fundamental set of functional dependencies. Okay, let's learn it with an example. For example, AC AROC is redundant in AB, BC, and AC. Parts of functional dependency that may be redundant are, for example, okay, some parts of the functional dependency may be redundant. For example, a given equation RHS, AROB, BROC, and AROCD can be simplified to AROB, BROC, and AROD. Why did we remove this C from here? Because we removed C from here because we are mapping A to D. Okay, let me show you. Mhm. What is the problem with this guy? We are mapping A to D. Okay, and not C. Why are we doing this? We are doing this because we have already mapped A to C. Uh, we have already mapped A to C when we mapped A to B and then B to C. Okay. Hence, by Armstrong's axioms, A directly maps C, whereas in this case, A does not map D. Hence, it is another functional dependency. It is another FD that has to be mentioned. All right. Let me remove this. If let's take another example. If A arrow B and B arrow C implies A arrow C. Okay, okay, yes. In reverse, A arrow B, B arrow C implies A arrow C. Okay. A arrow C, A arrow D implies A arrow CD. Yes, this is the transitive thing that we learned earlier on. Let's okay. So you have to check this twice in the forward manner and in the backward manner, in the reverse manner. So let's take another example for LHS. Uh, A arrow B, B arrow C, and AC arrow D. Can we simplify it? Can we simplify it? Mhm. So A again, A arrow B, B arrow C, and A arrow D. How did we reach there? Going through the forward manner, A arrow B, B arrow C implies that A arrow C and A arrows AC. Right? This line is important. This much is important. That A implies C, A arrow C implies A arrow AC. Yes. And now A arrow AC, from A arrow AC, we can imply that A arrow D. We can imply A arrow D directly. We do not need to write AC as a whole, and we can just write A here. We can just pick it up A, pick it up, and put it right over here in place of AC. All right. Let me remove this. Okay. And in the reverse order, A implies C implies AC implies okay, the same thing. Let's move forward. I hope you understood the two examples, example 1 and example 2. Canonical covers. Okay, so this is basically the same thing. Here the third, this much is deeply explaining this question, and the next slide is deeply explaining this question. That's what this is. All right, so let's skip these two. This is a pseudo code on canonical covers. Some more examples on this, and practice problems on functional dependencies. These are some practice problems that they asked us to do. Okay, so we can skip through these two. Okay, it is better. It is really good to see that it is recording perfectly and the display is working properly, because it would have been an heart attack for situation for me if it wasn't. Right. Give me a minute. I need to drink water. Where is the water bottle? Okay, so I'm back. Let's start again. I should have blacked the screen. It's my mistake. It's really better if I black the screen, so people watching it on YouTube, it's easier for them to understand till which part to skip the video. Okay, I think this much is good. Mhm, mhm, mhm. So the largest one that would come is this, right? If it can cover this, it will be able to cover all. Let's start. Consider a relation. Consider a relation R with the following attributes and a functional dependency with the following functional dependencies. How many candidate keys are there? Okay, similar question. Let's find the exhaustive set. So we need to cover all the attributes. We need to find the keys such that the closure set of the key provides all the attributes, right? So let's say I go with A. Okay. Now if I go with A, I can map H, and I can map nothing else, right? So let's leave A. Let's leave A. However, I can map H and A through GC. So if I take GC, take closure set, then what I can do is the result will contain GC itself, obviously. Then it will contain A, and through A I can also add H, right? Then what are the remaining attributes? A, B, C, G, and H. Okay, A, B, C, G, and H. So I would have to add B on both sides, such that I can cover all of them. So how many candidate key? This is a singular one, singular case, and two, two. Is there any other way? I don't think there is any other way I can reach it. So this is the answer, which is you know a singular candidate key. Let's go to question number two. I really need to learn how to manage this. So there is a relation with the following attributes and the following functional dependencies exist. Let M be the number of candidate keys and N be the number of super keys. Then what is the value of N minus M? What is the value of N minus M? So this is an interesting question. So let's firstly find all the super keys, and through those super keys I would be able to through those super key I would be able to find the candidate keys, right? So we need a function, we need a composite keys which maps out all of the attributes. It must map out all of the attributes, meaning, let's say I use uh, A again. So through A I can map nothing, but if I add B to it, I can actually map H. I can actually map H, and through AB I can also map C, and through C I can map G. All right. So this is one. This is one candidate key. Is there some other way? Is there some other way I can go through? Is there some other way I could solve this? I think we would need to use Chat GPT. Let's use Chat GPT to better understand the question and better, it will provide us with a better way to solve the problem. Let us go to Chat GPT, Baba. Chat GPT. I don't think this is how it's supposed to work. Usually it directly enters here. So pardon me, I am taking a few minutes. If that is the default, why is this coming up? This should be default, na? Okay, so I can, reach. Every time I open it opens Bing. This is really wrong. No worries. I can read GPT through here. GPT Baba, tell me where I'm wrong. I would need to check 24 or 21 as an answer, but I would not leave it out of the equation. So what this tells us is, see, through AB, C is a candidate key. Since it determines CG is a candidate key, and VH, since it determines both A and H, BG is a candidate key. Okay, let's find the super keys, the attributes in the relation. All the possible combination of can be super key. Okay, all the possible combinations of the attributes can be a super key. So ABCD is a super key, ABCG is a super key. We can map G and H. Can we map G through H? Is there some way? So from B we can map H, and from this we can also map C, and from C we can map G. So yes, we can map it. I think 24 is the correct 21 is the correct answer, but this requires a deeper explanation, which you can find out on by watching this particular video. Okay, let me tell you video to watch. Okay, planners attribute attribute set closure for D.B.M.S. You can watch this video of gate smashers plus the other video that you would be you need to watch is this, right? Super key and candidate key tutorials. This tutorial lecture, you need to watch it. Since I have not covered it in the in my video, because it does not provide us with any PPT, it is mandatory that you do this lecture. Let's go here and skip this question for now. Skip this question and this learn this on your own through this video and that this video. These two videos will help you find the answer to this question, because this is rather complicated to explain it in without pen and paper. Consider a relation EFGHI and the functional this. What is the closure set of E and F? Okay, what is the exhaustive set of E and F? So this is the relation. This is FD. So what we need to find is E F, right? What is the closure set of EF plus, right? EF plus. We need to find this. So immediately you would by default write EF because they are the subset of the given. Now from F we can map H. Let me change the color. From F we can map H. Hence H would also come. Now from you know is there something we can map through? Nothing. So it is simply EF and H. That's it. Consider the given set of functional dependencies. Consider the given set of functional dependencies. Okay, we are considering it. Choose all the correct options. So let us choose the correct options. So basically, all the options, contain extraneous attributes. So what in the end or the final, the mission is to remove all the extraneous attributes or to understand all the extraneous attributes. So let's start with this one, the immediate first one, E arrow fi, E arrow fi. Now this means that E individually maps both of these. All right, E individually maps F and E individually maps I. Okay, let me show you this. What we are looking for is something that we can remove. I don't think this one has anything to remove because none of these can be reached through anything that is present here in the rest of the set. All right, so let's move to another one. And since only one of these is required, let's find what is it. It's either E, F and H. Let's move on to the second one. Let me just encircle all of them so it's easier for us to differentiate between this hodgepodge. All right, so currently we are working on this one. FJ arrow H, FJ arrow H, FJ arrow H. So can we remove something? I arrows J, I arrows J. Okay, so you can read J through I, uh, and you can reach. Nope, nothing. There is nothing that we can do on F. There is nothing that we can do on F. Let's move on to this I arrow J. Let's what happened? Yes, let's move on to this I arrow J. But since it is not in the options, let's move further. Let's go to H. Let's go to H, meaning EH arrow G. So from here we know that through E I can reach Fi. I can reach Fi, and through Fj, through I can reach J. Through this I can reach J, and through this Fj, I can reach H. Okay, I can reach H. So this is something you should see. Considering E, keeping E in mind, we can reach Fi through E, and then through I can reach J. So Fi becomes Fj, and finally, Fj, through Fj I can reach H, and there is no meaning in writing HH twice. You know, meaning either it's uh, either it's H implies G, either it should be H implies G, or either it should be E implies G. Now our doubt is which one is an extraneous attribute, or which one should we remove, uh, as both of them are present in the option. So let's go to the PPT slides and see which are the ones to remove, right? So extraneous attributes, I think we had some questions. No, not canonical covers. Mm-hmm. Okay, so read this. By reading this, we can understand that H is an extraneous attribute and not E. Reason: using E, we can reach H, right? Using E, this one, we can reach H, but we cannot do vice versa. You cannot go from H to E. You cannot manipulate H into going to E. So this one is correct. This one is correct. Let's remove and move forward. Consider the two possible sets of functional dependencies on relation PQR. Okay, this is the relation with the attributes, and these are the functional dependencies. Okay, F1 has P arrow Q, Q arrow R, and R arrow P, and F2 has P arrow Q R, Q arrow P, and R arrow P, right? So we need so this is a question on canonical covers, right? It's better to read the PPT once. Let's read about canonical covers. So basically we need to convert the upper one into this. We need to convert this into this, removing all the extraneous attributes, right? Removing all the extraneous attributes. So can we remove R from can we remove R from here? Can we? Because Q would reach P. Let me see. Can we remove R from here? Because Q would reach P and R would reach P. Let's check. See, let's say I remove R, right? Let me remove R. So will P reach it or not? So P reaches Q, Q reaches P, and R reaches P. Let's move on to another question and return to this question later on. We will cover this question at last. Choose all the correct options from the following. For a given two set of functional dependencies, if F1 covers F2, F2 covers F1, then F1 and F2 are equivalent. Yes, this is true. Attribute closure can be used to find non-trivial functional dependencies. Let's see attribute closure uses. It would be under attribute closure uses. We used to find non-trivial functional dependencies. Can be used testing functional dependencies. I think we can use it, but let's leave it right now and come to this later on. A prime attribute is a proper subset of super key. Is there something known as prime attribute given here? Let's check this in chat GPT. What is a prime attribute? Let's ask him what is a prime attribute. What is a prime attribute? What is it? Tell me. A prime attribute within the context of database theory refers to the attribute that is a part of candidate key within the relational schema. In simpler terms, a prime attribute is an attribute that contributes to the forming of unique identifiers or for tuples in a relation. Yes. So it is something that while watching the Venn diagram, while watching this Venn diagram, we can also add another ellipse in this and write a prime attribute into it. Okay, we can add prime attribute into it. A closure set of a functional dependency is minimal set of functional dependency for that relation. A closure set of functional dependency is the minimal set of functional dependencies for that relation. No, it is not. Closure set is an exhaustive set, right? It is the exhaustive set of the functional dependencies. Consider a relation this. Consider a relation with the following attribute and functional dependencies these. The following functional dependencies. Now let's check GE, G, GH, and E. So let's check G first because it is singular. So G covers EF, G covers EF, F covers H, and GH covers IH. GH covers IH, meaning all of the attributes are one by one included in G, meaning G is a super key, meaning G is a super key. And if G is a super key, GE is also a super key. And is GH a candidate key? No, GH is not a candidate key. However, G individually could have been a candidate key. Let's check for E. Let's check for E. Let's check for E. So E maps F, E maps F, F maps H. Now F maps H, and yes, it stops right here. It stops right here because you need G to map I and you need G to map something else. So it just ends here, meaning that these two are correct and these two are incorrect. Okay, let's move forward. Consider a relation with the following attributes. Consider a relation with the following attributes and a set of functional dependencies with the following functional dependencies. Why? Okay. Choose all the possible functional dependencies that can be implied from F. That can be implied from F. What is the meaning of being implied from F? Let's again ask GPT Baba. Explain me the meaning of this line and add the line here. Okay. That can be implied. Okay, so basically, are they in this form or not? You know, if A implies B, B arrow C, then A arrow C. This is what they are saying. So A arrow B C, meaning A arrow B and B. Let me do this. A is mapped on to B and C, B and C individually. Now B is mapped to E and CD is mapped to EF. EF, right? So A through B is D mapped or not? So D is not mapped. Let me remove one singular thing that is it is correct but just not represented correctly, right? So CD represents E and CD represents F. Okay, so let me change the color. CD can reach E and F both, and since A can reach C, meaning AD can reach F. AD can reach F. Hence, this is correct. The first one is correct. Consider the relation this with consider the relation this with the following functional, FD dependency set. What are the which of the following are prime attributes? Let's check what are prime attributes. GPT Baba tell us examples on prime attributes. Okay, so prime attribute is something that is a part of candidate key, composite candidate key. So so what we need to do is firstly find a candidate key. Let's find a candidate key. So AB. Let's always start with the first one. AB can reach C. Now it is a dead end here. It is a dead end from here. However, if I add D to it, if I add D to it, I can reach C and I can reach E both. Let me check for any other one if I can. No, so D, A, and B are the candidate key. D, A, and B are the prime attributes, right? A, B, and D. All right. Let's move to the questions that we left. Let's ask ChatGPT to explain with another example. Explain this question with a simpler example first, and then solve the question itself. If every dependency f1 is also present in f2, this is an important line. F2 covers f1 if all the dependencies in f1 is also present in f2. uh, okay, so let me explain this to you in a simpler manner. F2 covers f1. Okay, f2 covers f1 if f1 if f1 is a subset of f2, is a proper subset of f2. That's what they are saying. That is when you know f2 will cover f1. That is when f2 will cover f1. Okay, f2 covering f1. Now if somehow we manage to do this, okay, if somehow we manage to do this, that f2 is also a subset of f1, right? If f2 is also a subset of f1, this both would together imply that these both would together imply that f1 is equals to f2. Okay, together they would imply that f1 is equals to f2. So let's check if f1 is a subset of f2 or not. F1 and PQR is present. Is P related to Q and R individually? That is true. Q is related to P, that is something extra, and R is related to P. So since R is Q is related to P, it is indirectly related to R. Hence, F2 will be covering. Let me do this here so it is easier for you people to understand, right? Mm-hmm. Remove it. Let's see what f1 demands, right? What f1 is saying. But now what f1 is saying, it's simple. Okay, I do not need to draw this, but let me draw this. So P determines Q and P determines R. P arrow R exists. Now a vice versa from Q to P also exists, meaning Q is indirectly related to R and R to P also exists. Okay, meaning R to Q also exists. So all we need is P to Q. Does P to Q exist? Yes, yes it does. Does Q to R exist? Q to R does exist. Does R to P exist? Yes, R to P does exist. And here we have the answer that F2 covers F1 F1 does not cover F2. Yes, even let me check. Let me check. Does F1 cover F2? For F2 to be covered, what F2 says is everything is related to everything, right? Everything is related to everything. It is basically a circle. You can reach from any point in the graph to any other point in the graph. So you can reach from Q to P, Q to R. You can reach P to Q, P to R. You start anywhere, you can reach anywhere. That's what F2 is all about. Does F1 is F1 the same? So from P to Q you can from P you can reach Q, and from Q you can reach R, and from R again you can reach P. So yes, this is a circle, meaning you can again reach. You can start anywhere and end up anywhere. So F2 does cover F1 does cover F2, meaning that F1 and F2 are in the equivalent. Consider the two possible set of F1. Okay, so this is a cyclic pair. This is a cyclic pair. Here P reaches R and R reaches Q. R reaches Q and Q reaches R. Okay, okay. So in this case, that what are the minimum number? What is the minimum number of functional dependencies that must be needed in that must be added in F2 to make F2 cover F1, right? What F1 is? F1 is P, Q, and R. Okay, that's what F1 is. So it is a cyclic pair. I think I have made a mistake here. Let me correct my mistake. Let me correct my mistake. Okay, it is a cyclic pair. P arrow Q, Q arrow R, and R arrow P. Okay, this is for F1. Let me write F1 here, so it's not confusing. F1. For F2, what we need, what we are doing is making F2 cyclic. F2 for F2. This is the wrong. You know, let's make F2 cyclic. F2. So this is P. This is Q. This is P. This is Q, and this is R. So P2R already exists. Okay. Q2R already exists. Okay. R2Q already exists. Okay. So what we finally need is a singular relation between P and Q, right? But we need to make it cyclic. We need to make it cyclic. So uh, we need Q to P. We need Q to P rather than P to Q. Okay, we need Q to P. Hence, making the function cyclic rather than P to Q, right? That would be wrong. So all we need to add is a singular functional dependency in F2 such that F2 starts covering F1. Okay. So I think I've covered all the questions. Let's check answers. Oh come on, I is this okay? So this is not how they should have done this. Okay, this is they played really dirty this time. Give me a minute. I have to search the answers. So let's check the let's do it orally. No, there is no way I can do it orally. But let's quickly do the questions that I know the answer to. You can just Luckily I am recording this, so I can just go to my channel and watch. Please, please, please. Yes, it is streaming. It is streaming. So all I need to do is go on the channel and check the answers. I'm recording this, so I can just go to my channel and okay. All right. So let's skip these two dependencies. Go through. Is there some other way I could solve this? I think we could chat GPT. Let's use chat GPT better understand. I'm just writing the answers down. Just wait for a few minutes. Let's check the answers. It is a good score. It is a good score. So okay. So C and D would also come here. It is perfect. The answer is perfect. Attribute closure can be can be used to find the non-trivial dependencies. This is something that we learned today. And a prime attribute is not a proper subset of super key. Okay. There are three candidate keys for primary key. Okay. I want you guys to do this question. Why? I immediately, told yes, there are three candidate keys for the primary key, but it's your job to find the answer to the fifth one. You can WhatsApp me. You can write the answer of this in the comment section. Uh, I would not be telling you this here. I would be telling you this in comment section after 2 days. I will be giving you 2 days to find the answer yourself. Okay. And this question is, let's leave this question for for a few times. I would be covering it this question up in the next session itself. I would be definitely covering this question because even I have some doubt. So if I have doubt, I won't be teaching you wrong concepts without clearing my doubts. So I think we have 9 out of 10, which is a really good score. Okay, so this is Suchita Sharma. I delivered what I told you. I delivered on my promise. This is my channel. Do subscribe. And this is me signing off. Good night and good morning for some of the people who would be staying awake. Okay, bye bye.